Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to demonstrate how to write force equations for objects undergoing circular motion. So first of all, we're going to talk about the simulation I've got running here. This is just a simulation of a basic pendulum that has a length of 0.7 meters and a mass of 1 kilogram oscillating back and forth. This green vector here represents the velocity vector at any given time. You'll notice that at the bottom the green vector is the largest it's going to be, and it's 0 at the endpoints because the thing's not moving. Now also notice that that green vector is changing in magnitude, therefore you have a tangential acceleration, but it's also changing in direction, which means you also have a centripetal acceleration. The yellow vector here, right, the one that's kind of going crazy here, that's representing the acceleration vector of this object. I'm going to just kind of pause it somewhere about maybe there. So at the instant shown, this object is moving kind of up and right, but it's slowing down at that instant. So the acceleration had a tangential component, which is opposite the velocity vector. Now, if you look really carefully, you'll notice these are not exactly parallel. We got it close to an endpoint here, which means the speed is very slow. The centripetal acceleration vector points towards the center of curvature, but it's going to be pretty small at that point because the speed is so low. So the acceleration at this instant is basically tangent to the curve. I'm going to go ahead and kind of slow this down. Keep it running. Oh, I gotta change my mode I'm working in here to do this. Oops. Alright. Well, having a little trouble slowing it down, having some technical difficulties here, so I'm going to just go ahead and let it run at full speed here. So, we're going to look at a free body more at kind of a mid-angle here. Maybe, let's try, oops. I want to back that up a little bit. Maybe about there. Oops. Let me get it back into motion here. Not where I want it. Good enough, right there. Alright, so I'm going to take a look at a free body of this object at this instant in time. Now you notice the velocity vector is pointing down and left. And remember, it was kind of coming back down, so this thing right here would be getting larger because it's speeding up. But it's also undergoing circular motion, so there's also a centripetal acceleration component that points this way, up towards the center of curvature. That's why our yellow acceleration vector looks the way it does. It has a tangential component and a centripetal component. Based on the orientation and magnitude of this vector, the tangential component is larger than the centripetal. I'm going to go ahead now and talk about how to write force equations for this object. So you start with a free body diagram, and I've already done this over here. We have a tension acting kind of up and left along this path. Now, the center of curvature is maybe about here. There's no reason to draw this tension vector that length. The length of this curve is not equal to the length of this vector. The gravitational force vector straight down as always. And you can write force equations in any set of coordinates you want, but the most convenient thing to do here is to write equations that are in the direction of our respective accelerations, right? So the tangential acceleration points this way. I'm going to go ahead and just call that the x direction, I guess, if you will. And the centripetal acceleration points this way. I'm going to go ahead and call that the y direction. Actually, you know what? I'm going to go back and rename those two. Tell you the truth. We're going to call this one the tangential direction, and we're going to call this one the normal direction, normal to the velocity vector. Now let's go ahead and start thinking about vector components. The tension is already parallel to this, nothing to worry about there. The gravitational force vector we can break into components. I like to use red for vector components. It has a component this way and a component this way. Here is an angle theta. This component is going to equal mg cosine theta because it's adjacent to the angle theta. This one's going to equal mg sine theta. Now it turns out you can go through the geometry here. It's pretty easy to show that this angle theta and this angle are the same. Any given, and that's true at any point along this curve. Now, actual numerical value here, it's probably listed on here somewhere. I'm not going to worry about it. I'm just going to call whatever this is theta. So when we write force equations now, we're going to write one equation for the normal direction. The reason for doing that, my standard rule of thumb, identify acceleration direction, call that positive. The centripetal acceleration points towards the center of curvature, which is here. So when we write a force equation for that, sum of all forces equals ma. We're calling up and left positive. We look at our free body, the tension is in that direction. This component of the gravitational force is also parallel to this direction. So we're going to have an mg cosine theta. Now I'm calling up and left positive, and this force vector is down and left. So we have now summed of forces in this direction. And by Newton's second law, that equals mass times the acceleration. Now this acceleration is a centripetal acceleration, which has a magnitude of v squared over r. In this case, the r would be basically equal to the length of this string, plus maybe a little bit more. It would be the distance from here to the center of mass of this object. All right, next equation to write. We can also write a force equation in the direction of the tangential acceleration. Sum of all forces equals ma, down and left positive. Remember my rule of thumb, identify the acceleration direction, call that positive. Let's go back to this picture. See this green velocity vector? And imagine it's in its downward swing. This green vector is getting larger in length, meaning that the tangential acceleration is down and left in that direction. So we look over here at our free body. This force vector does not have a component in this direction, in the tangential direction, only this one does, and that's equal to mg sine theta. And that's it, equals ma. Now this is not a v squared over r acceleration, this is the tangential acceleration. This acceleration has to do with changes in the object's speed. So this video is just to demonstrate how the acceleration vector changes direction in a circular motion problem such as this, how to take a look at a snapshot in time and write Newton's second law equations for the free body. So I hope that this has successfully done this for you. Have a great day.